Okay, so hopefully everybody's ready now for the final session, or the final talk of this morning's session. And it's very nice to have Mark McLean from Stony Brook University, and he's an expert in symplectic topology and algebraic geometry. And the title of his talk today is Birational Calabi-Yau manifolds have the same small quantum products. So let's welcome him.
Oh, apologies. Oh, okay. Okay, yeah, so if the normal bundle looks like this, then you can also do a similar kind of transformation. So you could, so it's, okay. So here's something that uses the Calabi-Yau property. So in general, birational morphisms are like, the sort of first example of maybe a birational morphism you see might be something like a blowdown map or something like this, where you, and there some sort of codimension one sort of region is collapsed to a point. But with Calabi-Yaus, you can make these regions where the birational transform is ill-defined of codimension 2. So they're not codimension 1, they're codimension 2. And morally, the reason is that if for instance, the region where the birational morphism was ill-defined was codimension 1, somehow the birational map would collapse that codimension 1 region and create some churn class. But the churn class is trivial, so you would have a contradiction. So we can assume that if you have two birational Calabi-Yau manifolds, that the birational morphism is well defined outside a complex codimension 2 region. Okay, and so in particular, we have isomorphisms between second homology and second cohomology groups. Because this is real codimension 4. If you have 2 cycles, and relations between 2 cycles are sort of 2 and 3 dimensions. They avoid a codimension 4 region. Okay. Oh no, this is upside down. Okay. So we have a question, which is what properties do birational Calabi-Yau manifolds have in common? So what properties do they share? So I already showed you one, the sort of second homology and cohomology groups are the same. But we can go further. So there's this nice result by Batirev in mid-90s. They have the identical Betti numbers. This is not obvious at all. In general, birational morphisms change the topology drastically. But as soon as I have this C1 equals 0 condition, the topologies are the sort of the Betti numbers are the same. So Batirev proved this using p-adic integration techniques, and then Kontsevich sort of found a sort of characteristic 0 thing, some arc space techniques. And this is called motivic integration, and it has some sort of connection with the sort of techniques I'll explain, Floer theoretic techniques, but that's maybe another talk. Okay, so this is one thing they have in common. Actually, you can show they have isomorphic integral cohomology groups. The isomorphism isn't sort of canonical or anything, but you can show that there is that there at least sort of there is an isomorphism between them, so they have the same torsion and so on. Okay, there are other things you could ask. There's lots of people have answered other questions, like, for instance, there's people who spend a lot of time trying to show. Another question is, do they have the same, say, derived categories and things like this? And this is a different story, which I won't explain here. It's for someone else to talk about. But I'll just be interested in the topology, just the cohomology. Okay. So even though the cohomology groups are the same, they're not the same as as rings. So the cut product structures are different. And I'm not sure who came up with the first example, but there's a book on Calabi-Yau manifolds by Friedman and example 7.7. So there's some, two birational Calabi-Yau threefolds. Sorry? Yeah, you can have torsion. Yeah. Okay. Yeah. So so you can't use cup. The cup products are different in general. However, motivated by ideas in physics, in string theory, Morrison in dimension 3 and Rouen in all dimensions conjectured that they have the same isomorphic quantum cohomology rings. Actually, they isomorphic, what we call big quantum cohomology rings. And then there's also this word up to analytic continuation. So there's a sort of some sort of, you know, they're not exactly isomorphic. You have to sort of analytically continue one to the other. So quantum cohomology is a deformation of the cup product. So, yes. I'm not sure. Yeah. The d-equivalence conjecture is sort of motivated by like mirror symmetry. Yeah. So. Yeah. Yeah. So. Well, I mean, it comes. Yeah. So you see, this is connected with the Fukaya category. So you know, at least you can recover, I think, big quantum cohomology from the Fukaya category in many. Yeah. So when you pass the mirror, there's some sort of analog on the derived side, and yeah. So it's like, yeah, but yeah. Okay, so Li and Rouen proved this in dimension 3. So essentially, in dimension 3, everything is sort of, basically everything is connected. It's a composition of these Atiyah flops. So you just need to work out how big quantum cohomology changes under one of these Atiyah flops, and then you're sort of done. And then another actually quite impressive result really is by Li, Lin, Ku, and Wang, who proved it for ordinary flops, which is a sort of, it's like a generalization of an Atiyah flop. So Atiyah flop, you have P1 in a bundle over P1, but ordinary flop, you have some Pn bundle over some base, and then some appropriate normal bundle, and then you have some sort of very similar kind of flopping transformation, and they proved that the big quantum cohomology rings are isomorphic, and they also did some of these people also did a sort of homogeneous curve counts as well and showed they're the same. So they did a lot. Okay, great. So I should tell you what small quantum cohomology is. So actually, maybe I should go back to the conjecture 1 second. So here they, in this conjecture, say they have isomorphic big quantum cohomology rings, but the title of my talk is small. So small is just a part of big quantum cohomology where you set some variables equal 0. And so I'll explain what small quantum cohomology is. Okay. So I need a Kähler form on my Calabi-Yau manifold. It's projective, so I can find some nice, say, Fubini study form that I restrict from Pn. And then I'm going to fix a field. That's my coefficient field. Just make it Q or something like this. And then I need a ring, the Novikov ring. So this is just power series. So power series where the coefficients are elements of my coefficient field, and the exponents are homology classes of X. Okay, so that's my Novikov ring. So quantum product is small. The small quantum cohomology is going to be an algebra over this ring, and it's a deformation of the cup product. And when you have a deformation, you want a sort of deformation parameter, and there's this T here. Okay, so this is some sort of completion of the group ring of H2. That's another way of saying it. Okay, and here I'm using omega, so it depends on omega, scalar form. Okay, so the next thing I'm going to do is make a choice. With the small quantum cohomology will be independent of this choice, but it just, for ease of making the definition sort of clear, it's good to just choose a homogeneous basis for cohomology of X with coefficients in my field K. And then I need to choose the dual basis. So the dual basis with respect to the sort of standard pairing, cup product pairing. And then, oops. Okay, sorry, I'm getting used to this thing. Okay, so small quantum cohomology is defined as follows. So as a module over the, it's a module over, as a module over the Novikov, so it's an algebra over the Novikov ring. And as a module, it's just cohomology. But then I have this product star. And I'm going to define star in terms of the basis elements. So the structure coefficients from these basis elements. So star is the unique product which is linear over my Novikov ring. And this is what the product looks like. So so A is my basis elements, AI, AJ, and the small quantum product of AI and AJ is this sum. And these are the sort of structure coefficients. So sharp M. So what's that? That's the number of elements of some moduli space of curves. Okay. So I count some curves passing through cycles corresponding to AI, AJ, AM. This sharp, geometers never count like normal people. They don't go 1, 2, 3, 4. They count like intersection numbers. So it's like an intersection number or something, right? Okay, so this is the number of genus 0 curves, or genus 0 really maps from P1 to X, passing through cycles that are Poincare dual to AI, AJ, AM. Okay, so those are my structure constants for my algebra. Okay. AM hat here. Or did I got this wrong? I got the hat in the AM the wrong way around. Okay. Okay. Oops, sorry. Okay. Good. So that's small quantum product. Okay. Maybe I'll say one more thing, which is if. Oh yeah. So there's another thing. This should really be M beta. So I should have put M sub beta here. So the curves here mapping to X represent the class beta. So this should be M sub beta. Here's M sub beta, and this map should represent the class beta. So if you look at, imagine you had no non-trivial curves, So then the only non-trivial part of the product would be when beta is 0. And the only maps that represent the trivial homology class are the constant maps. And in that case, you recover the usual cup product. So if you just, equivalently, if you sort of set t equals 0, you should get the usual cup product. Okay. Okay, so now let me state the theorem, the main theorem. So we have our two birational Calabi-Yau manifolds, x and x hat, and now I have to choose Kähler forms omega and omega x hat because the small quantum cohomology groups depend on omega and omega hat. These could be these forms are sort of not related in any way. Okay. And remember, I had these canonical, once I fixed my birational morphism between x and x hat, it induces these equivalences. So I'm going to, if I have a, say, cohomology class in x, I might think of it as a cohomology class in x hat. I'll be very sloppy with how where my cohomology class lives. Okay, and then, okay, so before I carry on, x and omega, once I've chosen omega x, I have a Novikov ring. And once I've chosen omega x hat, I have another Novikov ring. And they're different rings. But I want to say that the algebras are the same. That's what I'm trying to prove. And so I have to compare the two small quantum cohomology algebras. And so I have to compare the Novikov rings. And so the way I'm going to do it is via the intersection of both of them. Okay, so this is the intersection. I've spelled it out explicitly here. And here I'm using these identifications. AI is either an H2x or it's an H2x hat. And so I have omega x of AI and omega x hat of AI. Okay, so this allows me to define the intersection once I've made these identifications. So I have these Novikov rings and I have their intersection. And this will allow me to compare the small quantum cohomology algebras. Okay. Okay, so here's the main theorem. So there exists a graded algebra over the intersection of these Novikov rings, together with the following algebra isomorphisms over this. So the following algebra isomorphisms. So if I take this algebra Z and I tensor it with the Novikov ring associated to X, then I get quantum cohomology of X. And if I tensor with the Novikov ring associated to X hat, I get quantum cohomology of X hat. Okay? So that's the main theorem. So maybe the algebraic geometers, when they've proved sort of versions of this result, they say up to analytic continuation. So the way they do it is they have these two Novikov rings, and they sort of have a common region, but they also have sort of other regions where they don't agree, and you prove that the quantum cohomology converges away from that, and then once it converges, you can sort of analytically continue from one region to another. But here, this is a sort of maybe this is sort of more algebraic sort of thing. Okay. Okay. So at least Kontsevich announced that they have a purely algebraic proof of this result. I don't know. I don't think they've released this on arXiv yet. But half of this result is at least on arXiv, and they prove many other things. This wasn't the focus of their work. Yeah, so this is the preliminary arXiv result. Yeah. And then I want to just say something about some work with my student, Jaiji Kai. So you can generalize this. So you can generalize this. There's a more general conjecture. So if I have two smooth projective varieties, x and x hat, they're K equivalent if essentially the birational morphism sends the canonical class of x to the nth canonical class of x check. And to compare these canonical classes, you choose a common resolution, and when you pull back, they're the same. So this is called K equivalence, and again, you know, the birational morphism is well defined outside a codimension 2 region. So again, Rouen conjectured that any two K equivalent smooth projective varieties of isomorphic big quantum cohomology rings. And so I think the methods of my own paper, and from what I understand, the methods of Katsarkov, Kontsevich, Pantov, and Yu cannot solve this conjecture. They only know how to, they use the Calabi-Yau property. And in my paper, I very sort of strongly use the Calabi-Yau property. So I can't generalize what I do to this setting, but I have a student, Jaiji Kai, who's working on proving this, in proving this conjecture in a different way. It uses sort of Floer theoretic techniques like I do, and I'll explain in a minute, but it's different. I won't say any more. Okay. Great. Let's see the time. Okay. So I'll explain what goes on in an example. So let's assume we're in dimension 3, and we have some class gamma in H2. And let's assume that every subvariety representing gamma is isomorphic to P1 with this normal bundle. So I can do this Tia flop, basically. And in X hat, it represents minus gamma. Okay? And they're related by an Atiyah flop along these curves. So basically, I just have a bunch of P1s, and I Atiyah flop along them, and I get a birational morphism, and there's some assumptions. Okay? And then let's just look at the even part of... So the only sort of... Let's look at just the even part of quantum cohomology and these sort of only sort of really interesting degrees, which are sort of degrees 2 and 4. So we choose a homogeneous basis of H4, which and an A0 is the Poincare dual to gamma, and then we choose H2 classes, which is the dual basis. Okay, and so as I said, the sort of pretty much the only interesting product is from H2 to H4. So that's all I'll compare. Okay. So so my claim is that this algebra Z is isomorphic to the even. So the even part of the algebra Z is just cohomology of X over this Novikov ring, this intersection of these two Novikov rings. And here's the product. So this is just the definition of the quantum product. But now, I mean, this is just the definition of the quantum product. I should have used M here. Sorry, this sharp M is here. Sharp M beta. But with gamma, I insert this term just artificially. And that's how I define the structure constants on Z. Okay, so I just have some formula for what the quantum product is in degree 2 of degree 2 classes. And then to compare the quantum cohomology groups of X and X check, I just take this class A0 and I replace it with this. I replace it with some rational function of t to the gamma, and then I get quantum cohomology of X. And if I do this replacement, So if I replace A0 with this, I get quantum cohomology of X hat, and so that's how I compare them. Okay, so this is this is the idea of, this is what the equivalence looks like. So again, you don't have a direct isomorphism, but you have some algebra, and then you do some substitution, and one substitution gives you quantum cohomology of X, and the other one gives you quantum cohomology of X hat. Okay, so this is what it looks like. Great. Questions? Sorry, say that again? Oh, A0. Okay, let me go back. So A hat 0 is Poincare dual to gamma. A0 is the part of the dual basis. Okay, great. So then we obtain these isomorphisms by doing these substitutions. Okay? So this is what it looks like in the sort of three-dimensional, this particular three-dimensional example. Great. Okay, so I'm a symplectic geometer, and I'm using symplectic techniques to solve this conjecture. And it's probably my favorite Floer cohomology group, Hamiltonian Floer cohomology. So now I'm going to start with just a general closed symplectic manifold with trivial first Chern class. And you should think of X or X hat, one of my Calabi-Yau manifolds. Okay, so I have a Hamiltonian, and then I want to specify the generators of my cohomology group, and the generators are going to be called capped one periodic orbits. Okay, so this is a one periodic orbit of my Hamiltonian, together with a cycle whose boundary is that orbit. Okay, so I don't have all the orbits. There could be some, orbits that represent non-trivial H1 classes, but I'm just looking at the orbits with trivial H1, and then a capping that specifies why it's trivial, like how it's trivial. Okay, so I hope I drew a picture. Here we are. Here's a picture. So here's an orbit of my Hamiltonian, so some solution of some ODE, periodic, and then there's some, say, Riemann surface or whatever that caps it up. And it's just thought, but this capping is just thought of as a homology class. This is just, so if I deform this or change this or whatever, it's fine. Okay, it's giving you the same orbit. Okay. So those are the generators of my chain complex. Do I say anything about the grading? Oh yeah, I have an action functional. So this is So I'm going to have a filtration. I need a filtration on my Hamiltonian Floer group. So the filtration will be given by this integral here, which is the action function. So this is the functional whose critical points are these one periodic orbits. Great. Okay, so now I choose two real numbers, and I'm going to define Floer cohomology in the action interval A minus A plus. Okay, so the chain complex is the free vector space generated by cap periodic orbits whose action is in A minus A plus. So I missed a minus there. A minus A plus. Okay. So just, think generators are orbits satisfying some condition. And then, I need a differential. The differential is some matrix with respect to this basis. So the differential is a matrix with respect to this basis, and the entry counts solutions of this equation and cylinders connecting these orbits. And this is a hard equation to solve explicitly. So you have to use indirect methods to do any sort of computation. Okay, so that's Hamiltonian Floer cohomology in the action interval A minus A plus. So now I want to talk about symplectic cohomology, which was developed by these people, really Flerhofer, Zender, and Chiliback, and then Joel Groman and Umut Varalgunesh and Sarah Venkatesh have a sort of version which is closer to what I use. So this will be a group, an algebra I associate to any closed subset of my symplectic manifold M. And this is the definition. So what I do is I have my compact subset K, which I'm thinking of as this thickened line. And M is I'm thinking of as this line. And I choose a Hamiltonian that's less than 0 on K, and then it's really big outside K. And then I just take the direct limit as the Hamiltonian gets bigger and bigger and bigger. Okay? So that's what I do here. And then I take the direct limit as the bottom action interval goes to minus infinity, the inverse limit, and then the direct limit as the top action interval goes to plus infinity. Okay? So what this is trying to do is it's trying to select orbits down here. Somehow these orbits up here, they sort of disappear, morally at least. And the orbits that sort of persist in this definition should be the ones that are near to K. And it's sort of roughly like telling you something about the dynamics of the boundary of K, sort of near the boundary of K. So orbits near there, the boundary of K. So this is symplectic cohomology. Oh, so the map is called a continuation map. It's another count of cylinders, and there's another. You have a Hamiltonian H1 and a Hamiltonian H2. You choose a path of Hamiltonians, and you get some equation, and you count cylinders with that, and it depends on that path. Okay. Great. Oh yeah, so great. So this is symplectic cohomology, and it satisfies some properties. And yeah, so in my paper I work, hard to prove some of these properties. Some of them are easier than others. The first property is that it's an algebra, and it has a product called the Pantz product. Again, it involves counting sort of Riemann surfaces that look like this, satisfying some equation that looks very similar to the Hamiltonian flow equation. So that's actually not too bad. That's not too hard to define, at least in my paper. Okay. The next thing is I have a map called a transfer map. And if I have K1 is a subset of K2, then I have a map from symplectic cohomology of K2 to symplectic cohomology of K1. So it goes, it's like cohomology, it goes in the opposite direction, it restricts. Okay? So that's the second property. What's the next property? Oh, yes. We need to connect what we do with quantum cohomology. So symplectic cohomology of M inside M. So if K is equal to M, then we get quantum cohomology. Okay? So here, essentially what you're doing is setting the Hamiltonian to be 0. You can just pretend the Hamiltonian is 0. And then if you sort of think about what's going on, you get quantum product. So that pair of Pantz, the sort of ends close up, and you get a sphere, and they intersect cycles, and so you get the quantum product out of it. Great. I need a definition before I state the fourth property. So a subset A in M is stably displaceable if there's a Hamiltonian diffeomorphism of M times T star S1 to M times T star S1, so that the Hamiltonian displaces A times S1 of itself. Okay? So that's called stably displaceable. So what I like about this definition is you can have some subspace which is not displaceable for topological reasons, but when you cross with S1, it's topologically displaceable, because I can take this S1 and shrink it a bit, right? But you may not be able to do that in a Hamiltonian way. So an example of a stable, I'll talk about this in a minute, but an example of a stably displaceable set is like, say, Cpn minus 1 inside Cpn. So Cpn minus 1 is not displaceable because it intersects itself, but it's stably displaceable. Okay. So if the complement of M, if the complement of K, sorry, is stably displaceable, then this transfer map is an isomorphism. So somehow stable displaceable sets aren't seen by symplectic cohomology. So, you know, if I have some stably displaceable thing, and this transfer map will be an isomorphism. Okay. So, for instance, you know, so in particular, symplectic cohomology. If I look at SH4 and SH3 together, symplectic cohomology of K inside M is quantum cohomology. Right. So I can take M and I can take some, say, very large compact subset K whose complement is stably displaceable, and then this will be quantum cohomology. So, for instance, in the CPN example, I could take a really large ball in CPN, and I know that CPN minus 1 is displaceable, so I know the complement of this really large ball is stably displaceable, and so I get quantum cohomology. As a ring, yes. Okay, now I need some technical definitions. I'll try. I can't explain it all in the sort of limited time I have, but I'll try. So, you know, the way to remember this is just technical stuff. Yeah, it's because I don't think I can. But I'll try and explain some of it anyway. So, so an index-bounded Liouville subdomain of M is a codimension 0 compact submanifold, which I'll call D, so that there's a Liouville vector field pointing outwards along the boundary of D. So a Liouville vector field is a vector field that scales the symplectic form. So it's Liouville, it scales, yeah, it's a vector field that scales the symplectic form when you flow it. And then for any Hamiltonian whose regular level set is the boundary, there's only finitely many orbits. Oh, this is not right. There are only finitely many orbits of any given index in the boundary. Sorry. So there's something I forgot to mention, which is Flow cohomology is a graded group. There's a grading. You have to grade the orbits. You grade them by Conley-Zender index, and I can't define that here. But Conley-Zender index is a kind of winding number. So you have an orbit, you have a vector field, which is your Hamiltonian vector field, and you have an orbit, and you go round the orbit. And then you look at the sort of linearization of the vector field, the flow near that orbit. So that's like a family of matrices. And then you associate an index to this family of matrices. So for instance, if it's a family of unitary matrices, then you take their complex determinant that maps that to U1, and it's the winding number around U1, which gives you the Conley-Zender index. So this is of finitely many orbits of any given index in the boundary of D. Okay, so this is some technical condition, and I suppose if you're an algebraic geometer, it might be hard to process this in the talk right now, but just some very technical condition, and it's very special to our Calabi-Yau setting. Okay, and then if we have an increasing family of index-bounded Liouville subdomains, then this is an isomorphism. Okay, so basically, in a nutshell, this is some technical condition which allows me to show that I have an isomorphic, some transfer map is an isomorphism. Okay, and again, this will be very special to the sort of Calabi-Yau setting. This is where my proof would really break down if I went beyond Calabi-Yau. Okay, great. Oh, and then there's, yes, then there's another property. So the other property is if I have some subset of codimension 4, real codimension 4, so you think of W as like a subvariety of complex codimension 2 or higher, and then I have two symplectic forms in the complement of W and some appropriate complex structure, then and some index-bounded Liouville domain, then I can define symplectic cohomology over the intersection of these Novikov rings. Okay, I hope I drew a picture. Did I draw a picture? Oh, maybe I drew a picture later. Okay, so this again, this will be the axiom that will allow me to sort of compare Floer cohomology groups on different Calabi-Yau manifolds, and hence different quantum cohomology groups on Calabi-Yau manifolds. So I'll explain that in a minute. So again, this is another sort of slightly technical condition, but it's sort of needed to compare my different quantum cohomology rings. So one thing to say is that the reason why I need this codimension greater than or equal to 4 condition is Floer cohomology is defined with orbits, and then you have these cylinders connecting these orbits. And these cylinders are dimension 2. And so dimension 2 things don't intersect codimension 4 things generically, so they can sort of avoid this W. So this is why I have this codimension 4 region here. So, okay. Okay, so let me, using the axioms, just formally prove the theorem. So we have our two birational Calabi-Yau manifolds, and remember V and V hat are the regions where the birational isomorphism is ill-defined. And then what I need to do is choose a common affine subvariety of X minus V and X minus V hat. A common codimension 0 affine variety. So I take V and V hat and I enlarge them to like effective ample divisors or something in the complement. So the complements are the isomorphic. So I choose some common affine subvariety, some common affine Zariski open subset of X and X hat. Okay? And then, well, I have to do some technical things. So I can modify the Kähler forms without changing their cohomology class. So, and I can find appropriate index-bounded Liouville subdomains inside this affine variety so that there's an increasing family of index-bounded Liouville subdomains connecting D and D hat inside A, and X minus D is stably displaceable, and X hat minus D hat is stably displaceable. So, this is where I'm going to use one of the axioms, and this is where I'm going to use another one of the axioms. Okay, so this is a slight lie. I think I say it's a lie. Oh, no, yeah, so there's this. I also want the symplectic forms to agree near D. And to do this, I have an affine variety, and I do a lot of playing around with plurist subharmonic functions, if you know what those are. So there's a lot of plurist subharmonic sort of manipulation here. Yeah, this statement is slightly a lie. It's more technical than this. I think the statement's true, and I might be able to prove it now. But in the paper, this is not what I do. Yes? Which one? Here? Last line. No, oh, this is D. D, yeah. I hope I get that. I'm trying to see which way around it is. Yeah, D is the smaller one, I think, and D hat's the bigger one. So you have D, and then D hat, it grows bigger to D hat. But they only agree near D, the smaller domain. Okay. Let's see how much time. Great. Okay, so using the axioms, we can prove our theorem. So SH star D inside X by axioms 3 and 4 give me quantum cohomology. If you just sort of trace everything I've written. And SH star D inside X hat using axioms 3, 4, and 5 give me quantum cohomology here. 5 is the increasing family of Liouville domains, then giving an isomorphism. Okay, so once I've set up these properties, I just sort of can prove my theorem. And then I need to compare SH star D in X with SH star D in X hat, and that uses axiom 6. So the algebra Z is constructed using axiom 6, and it gives the isomorphisms as well. Okay, so that's the proof. So the key idea is using symplectic cohomology. Maybe I should say sort of morally what I'm trying. There's another ingredient. There's something hidden here as well. So I use axiom. Is it S? I've forgotten which one is the one where if the complement is stably displaceable, then I get an isomorphism. I think this was SH3, axiom 3. So I need to prove that the complement of D is stably displaceable. And that involves some effort. And essentially that involves proving that every codimension 1 or higher subvariety of a projective variety is stably displaceable. And so that involves some effort. It essentially uses an H principle. Some of you know what that is. But I spell it out in my paper. I can explain more. I think my proof is very hands-on, but experts have told me that there's a sort of just more direct thing I could have quoted or something. But I have a very explicit proof in my paper. Okay, so that's the proof of the main theorem. And then in the last minute, I can just ask for further directions. So if you're a Gromov-Witten theorist, you might be dissatisfied with the result because I just have an algebra Z and these isomorphisms, and I don't specify exactly how they are isomorphic. There should be some map. And at least over Q, the rational numbers, the map should be induced by the closure of the diagonal of the birational morphism. So you have X, X hat, and then you have X times X hat, and you take the closure of the diagonal, closure of the graph of the birational morphism. That's some cycle in X times X hat. And once you have a cycle in X times X hat, you have a correspondence. And that correspondence, at least over Q, should give you an isomorphism. If you use coefficients in another characteristic, it doesn't induce an isomorphism. There's flops, the Mackay flop, which won't give you an isomorphism, but at least over Q it should. So I have a student working on some partial results. And also, this word how, maybe we're thinking about a better description of what this isomorphism is in general. So this is just what I said. So conjecturally over Q, the equivalence is given by a correspondence. And this is the correspondence induced by the graph of the birational map. Okay. So it's a map from cohomology of X to cohomology of X hat, and it sends alpha to, you pull back alpha, intersect with the graph of the birational map, and then push forward and take the Poincare dual. Okay? So that's one further direction. I don't know if I have another one. Maybe I have another one. No, that's it.
Are there any questions, Mark?
Yes.
Thank you for the lecture. I'm wondering, you've introduced the axioms from 1 to 6. Yeah, and I want to ask, is that we developed the isomorphism between the symplectic homology and the quantum homology at the beginning or later in your paper? Yeah. I'm questioning about the axiom 3.
Okay, let's go back to axiom 3 so we can discuss it. Sorry, okay. There we go.
Yeah. Is that we develop these things at the very beginning or later in your paper?
So this is something this is a very small part of my paper because essentially if you just follow the definitions and you just use k equals m and you follow the definitions, essentially the Hamiltonians you're using are C2 small. If you have a C2 small Hamiltonian, it's a very classical result that this gives you cohomology, and this is what I'm using.
Oh, okay, thank you.
Yeah,
thank you.
Hi, Professor. Thank you for your talk. I may wonder it is possible for us to first, you see the small quantum cohomology basically saying the quantum parameter in H2, right? The tau is in the quantum product. The parameter is talking about the quantum product. Deformation is the parameter is in H2.
Yes.
So can we trace the H2 or the what tau of this X and of this Calabi-Yau and its birational? What's the correspondence?
I mean, the only way I know how to compare it is by the intersection of these Novikov rings. So,
okay.
Yeah, so...
You didn't trace the product parameter.
I mean... In some sense, the H2 is fixed, but the cohomologies are not identified in a very nice way. So this is how I've done it. So in some sense, they're just identified somehow, by this change. You have the intersection, and then you extend both ways. But the difficulty is the fact that I have a completely unknown sort of isomorphism between, say, Z and quantum cohomology, and so this is the
So as space, they are same, but they still have different elements.
Yeah.
But,
yeah.
Okay.
I mean,
sure.
Another further direction is the Crepin resolution conjecture, which is the orbifold case, and there you actually do if a lot of these ideas don't work because for instance in the orbifold case the transformation is not codimension 2 anymore. It's there's divisors and then I'd expect there to be a sort of change of Novikov parameters, and so again a sort of unknown change of Novikov parameters. So
I may wonder. Secondly, is it possible for us to show, or any other people working on it, to show the Frobenius manifold of if we restrict on small part is identical, or the quantum connection?
So
something like that.
So I think I spoke to some experts. So Hamiltonian Floer cohomology has a ton of structure. I had this pair of pants, but I could have Riemann surfaces with many ends, mapping to one end, and so I have this huge, intricate, really chain level structure, and this is something, and then if you add an extra piece of data, which is just artificial, called a trivialization of the S1 action, then conjecturally you should get, say, all genus 0 Gromov-Witten invariants, so big quantum cohomology, essentially. And if I choose a different trivialization of the S1 action, I have this sort of Giventhal cone, and it will give me a transformation between two different Giventhal cones, but this is all very conjectural, I think, this stuff. This sort of hard algebra that I don't understand. So, I feel like once this sort of, if someone can establish a relationship between this sort of, all these higher operations with Hamiltonian Floer cohomology along with this trivialization of the S1 action with big quantum cohomology. Once that's sort of set up, these techniques should enable you to show that, at the very least, the given cones are related by some linear transformation. But when I talk to experts, they said that this sort of thing is really hard. So,
thank you.
Okay, do we have any other questions?
Sorry, this might be related. Naive question is that because this is Hawkshaw cohomology of the scale category, so is it possible to show the scale category?
Well, so the only thing about the Fukui category is, first of all, it's very sensitive to the cohomology class of the Kähler form. But it's also very sensitive to the Kähler form itself. If I deform it, you might have a Lagrangian, it might just sort of disappear or something.
Yeah. So maybe we can find a corresponding Kähler form on.
Yeah. So maybe what I think could be true. You see, again, there's a sort of mirror story. So but maybe what you would expect is that you have the Fukui category of X and the Fukui category of X hat, and they're sort of joined by some sort of family of categories, so some sort of analytic family of categories that connects one to the other. It's a bit like with so with like derived categories, if you have a derived category of a manifold and you change J, the derived category changes. It's a bit like that.
Yeah. So can you go to the last slide?
Oh yeah. Okay. Sorry, I did it. Okay.
Yeah. So this approach seems very similar to Worm-Woodward's approach using producing a map between a quantum homology using Lagrangian correspondence.
Yeah. So I don't want to. This is what I'm tasking my student with. So I don't want to. Yeah, it's all videoed, but that's why I want to try and get my student to attack.
But that is related, right?
Yeah. So I think that there should be some sort of quilt thing which maybe relates the two groups, some sort of quilt kind of map.
Okay, but the closure of the graph, is it smooth or?
No, it's not smooth.
Okay, that's.
Yes, there's problems. Okay, so let me find the axiom. So there's several axioms that fail. So 6 fails, but also but maybe the biggest failure is 5. So I have an increasing family of index-bounded Liouville subdomains, whatever that means. Index-bounded, to define index in the first place, you need Calabi-Yau. You need a trivialization of the canonical bundle. And so the index-bounded doesn't even make sense. And also, if I just have any increasing family of Liouville domains, I may not get an isomorphism. There are examples where, the rank of symplectic homology jumps, changes. It might just, it will start being equal to quantum cohomology. Like with CPN, if you have a large ball, it's equal to quantum cohomology. And then when you shrink the ball to, say, half the size, it jumps to 0. And so, this isomorphism fails. And in the proof, I have some really large Liouville domain corresponding to X hat, and I shrink it to some really small one, sort of relative small one, corresponding to X somehow. And so, I need that map to be an isomorphism, and it fails miserably. And so, as I said, my student has a sort of workaround. But this is different, it's completely different.
Okay, thank you.
Okay, well, I think we okay, but if it's quick.
So you talk about symplectic homology with a fixed ambient simplified manifold and they're related to some compact subset. So what if we change the ambient manifold? Do we have some, does this axiom still survive? Or
Sorry, what do you mean? So you change?
So your ambient manifold is fixed, right? It's always fixed. The M.
M is fixed, yes.
So we cannot change M, right?
No, the only way I know how to change M is this axiom 6. It's essentially, I'm removing W from M, and I'm replacing it with something else. And so somehow 6 is where I kind of change M, but it's a very special axiom. In general, I don't, like if I have two symplectic manifolds and a common Liouville domain and the complements are both stably displaceable, I don't have no idea what to do. Right? They're probably different. I just don't know.
Okay, so I'd say we've run out of time, unfortunately, now, but if you have more questions, then probably try and find Mark or come up and speak to him afterwards. But let's thank him again for a very nice talk.